So can you tell me which question?
Sir, just a second. I'll try to. So last question of 2004.
ISI?
Yes, sir.
Is this the one?
Yes, sir.
So an is 1 by n, bn is 1 by n plus 1. Okay, so I have to find this sum an minus bn upon an bn. All right, an minus bn whole square. So an minus bn whole square is simply an square plus bn square minus 2 an bn, right? Whole divided by an bn. So this summation. So this summation can be written as summation an by bn plus summation bn by an minus summation 2. Right now, what is summation an by bn? So summation an by bn is summation 1 by n upon 1 by n plus 1 plus summation 1 by n plus 1 upon 1 by n minus, you're going from 1 to 99. So what do you get when you add 2 99 times? Right, so you're just adding up 290 from 1 to 99. So this is just going to be 2 into 99. Right, so this part is 198. So this is summation n plus 1 by n plus summation n upon n plus 1 minus 198. So this is going to be, yeah, how could you solve this? Should we cross multiply this? Maybe we could cross multiply it. Yeah. All right, let's just write it down. Summation n plus 1 upon n. So this is going to be equal to n goes from 1 to 99.
So can this
So
be written as by separating the denominator?
yeah, you can try different techniques, whatever works. At the end of the day, there could be different techniques to do it. Uh, so let me try this one, plus 4 by 3 and so on till 100 by 99 plus what is this going to be? This is going to be 1 by 2 plus 2 by 3 plus 3 by 4 and so on. Okay. Now what I can do is maybe write a few more terms that would probably clear it up. 4 by 3 plus 5 by 4 plus so on till 100 by 99. And this will go on till uh, 99 by 100. Okay. Now let's look at the common things. What is 3 by 2 plus 1 by 2?
2.
Very good, 2. What is 4 by 3 plus 2 by 3?
2.
Very good. And so you see the pattern, right? 5 by 4 plus 3 by 4, 2, and so on it will go. Okay. This thing I've already written as 2. So, uh, so you'll wrap up everything till this point. Okay. So this penultimate number here is going to be 98 by 99 plus 100 by Yeah, plus 99 by 100. So you're going to wrap up everything till this point as 2. So you'll have 99 twos here. You'll have 99 twos here. So corresponding to each number here, you will get a 2. Plus, you will have this 99 by 100 remaining. So you'll have 99 twos plus 99 hundreds minus you already have 198. So that is something which will cancel out with all these twos. So you'll be left with 99 by 100.
Yes, sir.
Okay. So in a question like this, all that it takes is some hit and trial. There's no one correct way uh, or the fastest way, whatever comes to your mind. Next.
So this question number 5 of 2006.
Okay. Actually, this is a property. I mean, the proof is too technical. It requires to do a bunch of other theorems from stats, which I'll not be doing even in stats. Uh, so, I mean, this is something they used to ask earlier, but recently they have not asked it, so I've removed it from the syllabus. But if you want, you can just go to the proof and check RMS, AM. Mhm. Yeah, so this is, even I don't remember this proof particularly because I stopped teaching it a while back. But you can go online and find this result. If you can remember it, maybe that would also be sufficient. That RMS is greater than equals to arithmetic mean, greater than equals to geometric mean, greater than equals to harmonic mean. So this is a property which I don't know. I've never seen it being used. The reason is that RMS is something which is used a lot in physics and not in economics. Root means square. So this is basically root of mean of the squares. So you square things, then you take its mean, and then you take the root. So that is RMS. So if you could remember this, maybe it would come handy, but they have not asked anything related to RMS since this. So RMS greater than equals to AM greater than equals to GM greater than equals to HM. This part is something which you need to remember because AM, GM, HM are strictly speaking just mathematical things, but RMS is very important for physics, not for us. So RMS is greater than AM when numbers are not all equal. This is true. It is going to be equal if numbers are same. I mean,
Okay, sir.
no wait.
So this is basically based upon the property only.
No wait. RMS when numbers are same would be a square plus a square by 2 under root. Yeah, so that is going to be. So if you have the same numbers, RMS will be equal to AM. So the equality always holds if the numbers are same. If the numbers are different, then it becomes a strict inequality. Yeah, what were you saying?
So this is nothing but the property only.
Yeah, the proof is there. The proof is there, but proof requires a few more things, which we will not be doing even in stats. A few more theorems are required to prove this. AM greater than equals to GM greater than equals to HM. This is something which is not that rigorous to show, but showing RMS greater than AM requires a lot of mathematical rigor. So we'll not do that.
Okay, sir. So ISI 2014 first question. This question number 21.
In period 1, a chicken gives birth to 2 chickens. So there are 3 chickens. Okay. In period 2, each chicken born in period 1. So this is T equals to period 1. Okay. Period 1, there was one chicken who gave birth to two chicken. In period 2, each chicken born in period 1 gives either gives birth to two chicken or does not give birth to any chicken. If a chicken does not give birth to any chicken in a period, it does not give birth in any subsequent period. So a chicken could be either fertile or infertile. So continuing in this manner, in period K plus 1, a chicken born in period K either gives birth to two chickens or does not give birth to any chicken. This process is repeated for T periods. Assume no chicken dies. After T periods, there are a total of 31 chickens. Okay. Uh, each chicken gives birth to two chickens. In period 2, each chicken born in period 1 either gives birth to two chicken or does not give birth to any chicken at all. Chicken. Okay. So this was chicken 1. He gives birth to two kids. Okay, chicken 2 and chicken 3. Then each of them could either give birth to two chicken or they could basically be infertile. If both of them are infertile, then everything stops, right? So there would be no more kids here onwards. So not all chickens can be infertile in any period. So the least time required to reach any population would be, so least time required would be when all chickens are fertile. Okay, so they have asked me the maximum and minimum possible values of time period. So the minimum time required to reach 31 population would be if everybody is fertile. Okay, so if everybody is fertile in period 1, you have one chicken, then you add four, then you add two in the next chicken, so total becomes three. Then each of these two chickens gives birth to two more chickens, so you add four. So the total after this period becomes 4 plus 2 plus 1, 7. Then each of these four chickens gives birth to two chickens each. So 7 and 8 is 15, right? And then each of these 8 chickens give birth to 16 chickens. So the total becomes 15 plus 16. So that is 31. So period 1, 2, 3, 4, 5. So the minimum time is 5, right? So, so minimum time would be 5 periods. Period 1, period 2, period 3, period 4. Okay, no, 4 periods, sorry. This is the final stage in which birth takes place, right? So in period 1, chicken gives birth. So this was period 1, this was period 2, this was period 3, and this is period 4. So in period 4, the 16 new chickens are born, and in period 4, the total population reaches 31. Now the minimum time would be when only one chicken fertile in each period, right? So in each period, no matter how many chicken are born, only one of them is fertile. So you start with one in period 1, then this one chicken gives birth to two. Total becomes 3. Now in the next period, out of these two chickens, one is fertile, he'll give birth to two more chickens. The other guy is infertile, so he'll not give birth to any more chickens. So total becomes 5. Then two more are added, so 7. So you see, this becomes a arithmetic progression: 1, 3, 5, 7, 9, 11, 13, and so on. Okay, so this is the population in period 1. In period 1, the new chickens are born. So the total population in period 1 becomes 3. In period 2, this is the population. In period 3, this is the population. So population in period T is basically 2T plus 1. You see, 2 times 2 plus 1 is 5, 3 times 2 plus 1 is 7, and so on. So the sequence is 2T plus 1. Now 2T plus 1 should be equal to 31, which implies T must be equal to 50. So the maximum time is 15, the minimum time is 4. So 15 and 4 is the answer. Next.
So the question just which follows it. Yes, sir, this one. 24.
Okay, summation. Ah, log 3. So this just becomes minus a log 3 by k log 3 minus 1 to the power k minus 1 into this k can be taken outside. So k log 3 by k square. So this becomes minus 1 to the power k minus 1 log 3. Right. So now I have to add this up. Sorry, by k. Okay. So summation, I can take log 3 outside. So log 3 summation minus 1 to the power k minus 1 upon k, going from k equals to 1 to infinity. So here we will use the formula for expansion of log x. So the formula for expansion for log x is expansion. Should have given it in one of the notes. Yeah. So the expansion for log x is x minus 1 to the power n upon n summation. Okay, so the expansion for log x is ln x is equals to summation n equals to 1 to infinity x minus 1 by x minus 1 to power n upon n. Right? Focus on this part. Focus on this part. Right? Uh, so minus 1 to the power k minus 1. So this k minus 1 here, it's similar to this n here. There's just a difference of one negative sign. So what I'll do is I'll take one k outside. Right. So what I can do, I want to convert this into this format. Obviously, there's discrepancy here. There's minus 1 here and things are different. After I do some, I want to do some changes to this formula in red so that it starts looking like the formula in where was I? Yeah, this is log x. Hmm. So let's do 0. For x equals to 0, this would look like minus 1 to the power k minus 1. This would basically be okay, let's multiply this with a negative sign. So this becomes equal to summation minus 1 to the power k upon k. And since I've multiplied it with a negative minus 1, I'm going to take a minus 1 outside. Right? So this becomes summation minus 1 to the power k upon k. So this would be -1. So it should be x equal to 0. This looks like minus log of 0 minus 1 minus 1 summation 0 minus 1 to the power k upon k. So 0 minus 1 to the power k, right? So x should be equal to 0. So minus 1 log 0.
The log 0 is not defined.
Yeah, so that's what I'm thinking. Where did I make a mistake? This answer was log of 2. Let me check the solutions. This is what question number 24. Okay, this is not 2014. It's 2014. Okay, I messed up the solution, I think. Right. Hmm. What have I done? Why is this question? So let us have a look at it again. -1 is used to be log 2. So 2 minus 1 would be plus 1. X minus 1 to the power n. Log 2. Hmm. Yes, there's some mistake in this definition. Why is this definition not matching? Okay, so this definition, according to this definition, our answer would work. Maybe this definition is wrong. And see definition of log x, log expansion. Ah, yeah, that's the mistake. Okay, so you have a -1 to the power n minus 1 times x minus 1 to the power n upon n. So that was the mistake. Yeah. Okay, fine. So this definition is -1 to the power n minus 1. This is a complete definition. We'll be doing this expansion later on again, so I'll give it in notes. I mean, it could have been better if I did it later. But anyway, so this is the expansion of log x. Now, if you substitute this x equals to 2 here, right? So for x equals to 2, you see that this becomes just summation of -1 to the power n minus 1 upon n, right? For x equals to 2. So log 2 is the expansion of this part. So this is just log 2. So the final answer becomes log 2 into log 3. So that is this one.
So this question is not a part of
Which question?
question 24. Does not it directly belong to some?
I can't hear you properly.
Sir, am I audible?
Yeah, now you are.
So, sir, this question is not particularly related to sequences and series, but logarithmic expansions too.
Yeah, yeah.
Oh,
It's
okay.
related to that more than this. Actually, I actually saw the word series and I thought, yeah, maybe it's relevant. I should not have added it, but it happens sometimes. And when I'm collecting the problems, I see, okay, this is an infinite series, so maybe it fits in here. Anyway, next.
Number 55 for 2007 DSC. So,
Okay, the set, uh,
run this question. Maybe I have the
no, question 55 or 45?
2008, question number 55.
2008, question number 55. This one?
Yes.
Okay. Let GA be the function such that GA of x is equals to 1 if x is A, and GA of x equals to 0 if x is not in A. Consider the infinite sequence of functions fn where fn of x is equal to. So there's some set A of real numbers. So on the real line R, you have some set A. Suppose this is a set of real numbers in which you have the set A. So the g function takes a value 1 here, it takes a value 0 here. Consider the infinite sequence of functions fn where fn is equals to n times g of the set 0 to 1 by n of x. Okay. So on the real number line, this is the set 0, this is, let's say, 1 by n. So the function g of 0 to 1 by n of x, it will look like this. So for this function, the set A that I'm going to consider is 0 to 1 by n. So this function will look like this. Okay, so this is g of 1 by n. So if you take n equals to 1, this becomes g of 1, 0 to 1. Okay, so this is g of n, right? G of 0 to 1 by n. Similarly, if you want to talk about for n equals to 1, so g of 0 to 1 by 2, use a different color. G of 0 to 1 by 2 of x would basically look like this. 0 till here, 1 here, till half, it will take a value 1 and then again becomes 0. Okay. Similarly, g of 0 to 1 by 3 will be like this. Smaller than this, definitely smaller than this. And then here. Okay, so the g function takes a value 1 on a smaller set as n keeps on increasing. Now, what is fn? Fn is n times this. Okay, so the function f of 1, okay, let me use similar colors now. So function f of 1 will be n times this function. So n times this thing. So function f of 1 will basically look like on the Cartesian plane. So as you can see here, for n equals to 1, the function g is taking a value 1 between 0 and 1, and everywhere it is 0. So the function f of 1 will be 0 on account of the function g everywhere apart from 0 to 1. So it will look like this between 0 and 1. apart from 0 and 1. And between 0 and 1, it will look like function of n. So n is basically 1. So it will look like 1 here. Okay. Now f of 2 is 2 times g of 0 to half. So it will again be 0 here and 0 here. But between 0 and half, it will take a value 2 now. So if I were to plot these different functions on the Cartesian plane, they would look like this. So this is, let's say, 0, and this is, let's say, 1. This is 1 by 2. This is 1 by 3. This is 1 by 4, and so on. So the function f1, it will look like this. 0 everywhere except here. This is going to be f1. f2 is going to be 0 everywhere, but 2 between 0 and half. Right? f3 is going to be 3 between 0 and 1 by 3. f4 is going to be 4 between 0 and 1 by 4, and so on. Right? Do you get the idea? Everywhere else, these functions are 0, apart from what I've drawn them like. I don't know why they give such complicated things. They used to do that in the past. Maybe they do that again. So maybe when this question came, a lot of people didn't even know how to figure out what this is. This is not coming from any particular theory that we have to study. It's nothing like that. You just have to look at what would be the graphs of this function. Okay. Now for every x, the sequence of numbers fn of x has a limit in the space of real numbers. Okay, so yeah, so for every x, the sequence of number has a limit in the space of real numbers. So now you consider any x. Let us look at all the options. Limit n tending to infinity fn x does not exist for any x. So this is obviously false. This is obviously false. B part is obviously false because it's saying that limit n tending to infinity fn x does not exist. So let us take x equals to 2. Now for x equals to 2 here, every function is 0. Right? So f1 at 2 is 0. f2 at 2 is 0. f3 at 2 is 0, and so on. So limit n tending to infinity fn of 2 is 0. So the limit does exist for some x. So it's saying that limit does not exist for any x. This is false. Now limit n tending to infinity fn x exists. So when it exists, so let us look at different values of x, what will happen. So for any finite value of x here, let's say you take x equal to 1 by 10. All functions till f10 will be positive after f10. If this say, let's say this is your f10 value. After f10, no function will report a positive value here. So for all n greater than 10, fn of 1 by 10 is 0. So consider the sequence fn of 10. Sorry, fn of 1 by 10. Consider the sequence fn of 1 by 10. What is f1 of 1 by 10? What is the value of function f1 at 1 by 10?
0.
Sorry?
0.
No. This is my function f1. What is its value? This is my function f1, this is my function f2, this is my function f3, this is my function f4, and this is 1 by 10. So what is the value of the function f1 at 1 by 10?
1.
1. What is the functional value of f2 at 1 by 10? This is 1, 2, 3, 4, and so on. 2. Yeah. Similarly, it will go on. F3 at 1 by 10 will be equal to 3 and so on. But the last point would be F10. F10 at 1 by 10 will be equal to 10. F11 onwards, every function will have a value of 0 at 1 by 10. Right? So F1 by 10, F10 onwards, no function is going to give a positive value. So this is, let's say, F11. So F11 looks like this, 0 till here, then 11 here, then again 0. So this is my function F11. So for F11, the functional value at 1 by 10 is 0. So for all x positive, there exists an n such that, there exists a natural number capital N such that Fn of x is equals to 0 for all small n greater than capital N. So take any positive x here on the x-axis. After some point, all the functionals Fn will be 0 at this. So no matter what x you take, as long as it is positive, the sequence Fn of this number x will look like a set of numbers followed by a lot of zeros. So any such sequence will have a limit of 0. So it will have a finite non-zero elements, and after that it will have infinite zeros, any x positive. So limit n tending to infinity Fn of x is equals to 0 for all x not equal to 0. Now let us consider what happens to the limit at 0. So Fn at 0, consider Fn at 0. So Fn at 0 is never equal to 0. You see, no matter how large the n is, this will keep on contracting, but it will never be non-existent. So this sequence Fn of 0 will basically look like 1, 2, 3, 4, 5, and so on till infinity. So limit n tending to infinity Fn of 0 is actually does not exist. Okay, so for 0, Fn of 0 does not exist. For all other things, it is 0. So now let's look at the options. For every x, the sequence has a limit in the space of real numbers. This is false because it does not have a limit for x equals to 0. Limit n tending to infinity does not exist for any x. This is also false. It exists for every x apart from 0. When limit exists, the actual limit depends on x in the function. No. When limit exists, the limit is equal to 0. We saw that, right? The limit is always 0 whenever it exists. D is limit exists for all but a finite set of real numbers. So this is true. It does not. The finite set of real numbers for which does not exist is the set C. So obviously, a very complicated problem. In exam, if you get such a problem, maybe the best thing would be to leave it, focus on the other ones. But right now, the aim is to be able to understand all such problems. Okay, next.
Yes. So, sir, the best way to do such types of question is to draw
Leave
the
it.
graph first.
There's no one strategy really. I mean, maybe some other person would choose another strategy. I like to teach by graphs because students learn by graphs better, right? I cannot be like, I mean, I'm thinking of it. So in my mind, I have different visualizations to solve it. Teaching is different than solving. So what works for you when solving might be different. Maybe you can do it without doing graphs. Maybe somebody who's very smart was able to do this problem without any graphs. So I'm not sure. But I rely on graphs heavily because then you guys can understand it. Graphs are going to be time consuming in exams, especially in a objective exam. You don't get any marks for drawing graphs, no additional marks. So you can do it without graphs. Why not?
Okay, sir. Sir, question number 7 from 2009.
7 from 2009. I mean, you mean 2010, I guess.
Uh,
The
yes.
sequence -1 to the power 1 plus 1 by n. Okay, so this is basically -1. So let's start the sequence. Have you written down the sequence? This is basically n plus 1 upon n, right? So if you write down the sequence, so -1 times 1 plus 1 by 1 plus 1 times, sorry, so I'll just add, I write plus and minus alternatively, right? So
So
minus, yeah, you're telling.
2, -2, 1.5, -0.75.
No, no, you do not write them. You should not write decimals. Never write decimals. It is
Okay, sir.
not going to help you. -4 plus 1 by 4 and so on. Right? So now this is minus of 2 by 1 plus 3 by 2 minus 4 by 3 plus 5 by 4 minus 6 by 5 plus 7 by 6 and so on. Right? Okay. Hmm. So now I want to find its limits. Let us club the negatives in one side. So when I club the negative, it's going to be, and club the positives. So 3 by 2 plus 5 by 4 plus 7 by 6 plus 9 by 8 and so on. Plus, sorry, minus of uh, 2 minus 4 by 3 minus 6 by 5 minus 8 by 7 minus 10 by 9 and so on. No, plus. I've taken the minus outside. Okay. So what does this look like? If I cross multiply, actually not cross multiply. Maybe I add the remaining things, 4 by 3 plus 6 by 5 and so on. And I subtract the same thing, minus 6 by 5 plus 8 by 7 and so on. So I've added and subtracted the same thing from the entire thing. So the sequence on top becomes 3 by 2 plus 4 by 3 plus 5 by 4 plus 7 by 6 plus 9 by 8 and so on. Minus 2 plus or twice of 1 plus 4 by 3 plus 6 by 5 plus 8 by 7 plus 10 by 9 and so on. Let's focus on this sequence. So this sequence is going to be It's not telescopic. It's not going to telescope. It's not telescopic. Okay. So let's not do that. Let's try some other strategy. Minus 1 to the power n.
So what if we limit to infinity n tending to
I
infinity?
can't hear you. I mean, your voice.
So what if we take limit n tending to infinity? If we apply the limit,
They have applied the limit n tending to infinity because the sequence always goes to infinity, right? So they are asking you for n tending to infinity. So let us break it up. So this becomes minus 1 plus 1 minus 1 plus 1 minus 1 plus 1 and so on. Plus minus 1 by n plus minus 1 by n plus 1 plus 1 by n plus 2, 1 by 1 minus 1 by 2 plus 1 by 3 minus 1 by 4 plus 1 by 5 and so on. Okay. Now this sequence, it does not have a limit. This does not have a limit. Because you see, it is minus 1, then you add another n, it becomes 0. Then you add 3 numbers, it becomes minus 1, then it again 0. So this is a sequence which oscillates between 0 and minus 1. It starts from minus 1, then becomes 0, then minus 1, then 0, then minus 1, then 0, and minus 1. Now, if you can show that this thing has a limit, then something which doesn't have a limit plus something which has a limit will not have a limit. Okay, so let us look at this part first, and then we'll come to why this is going to be true. So 1 minus 1 by 2 plus 1 by 3 minus 1 by 4 plus 1 by 5 and so on. Okay, so this is basically 1 plus 1 by 2 plus 1 by 3 plus 1 by 4 and so on. Wait, they have asked this for the sequence. Oh no. Oh no, no, no. Forget everything. I did it all wrong. I'm doing series. I started doing series. They have not asked me to add them up. Oh, this is terrible. They have just asked the sequence. I'm doing this for the series. Let me just. The series is very simple, right? The series is very simple. The series is for n tending to infinity, the series just becomes minus 1, 1, minus 1, 1, and so on.
so
Right?
sir, basically it
For
will have two values, minus 1 and 1, so limit does not exist.
yeah, exactly. It has no limit points. Exactly, it has no limit points. Sorry, I don't know why I started doing addition of things. It's a sequence, so I should not have added it. Anyway, this is all wrong. So it has no limit points. It's another way of writing the sequence minus 1 to the power n. You add this 1 by n, but you know it's going, this 1 by n is going to 0 anyway, so it doesn't matter. Yeah, next.
Okay, sir. So question number 32 of 2015.
As n goes to infinity, the sequence, again, same question. This is 1 plus 1 by n. Right, so absolutely the same question. Instead of writing 1 by n, they have written n to power minus 1. So it does not matter.
And so question number 8 of 2018.
A sequence xn converges to x, consider the following claims. The sequence xn plus 1 upon xn converges to 1. The sequence xn plus 1 converges to x. Statement 2 is true for sure, right? Because if xn is converging to x, then xn plus 1 is also converging to x. You're just starting from the second term. You're eliminating the first term, right? But what, even if you eliminate a finite number of terms, nothing changes about the nature of the sequence. Is this much clear?
Yes, sir.
Okay, so if xn is converging to x, xn plus 1 is converging to x, then xn plus 1 should be converging to x. So this is now coming to this sequence. Yeah, it would be true if the sequence is not something going towards 0, right? So you could have the sequence xn is equals to 0, 0, 0, and so on. Or it becomes 0 sometimes in between. So in that case, xn plus 1 will also be 0, 0, 0, and so on. But xn upon xn plus 1 will not be defined. So the sequence converging to 1 is not true. This is not true because xn could become 0. But if you were to eliminate the zeros, then yes, this would be true. If you say that xn or xn plus 1 are never 0 and their limit is also not 0, even if the limit is 0, that is not a problem. Okay, you can take the sequence xn equals to 1 by n. Then xn plus 1 becomes basically 1 by n plus 1. So xn upon xn plus 1 is basically n plus 1 by n, which is basically 1 plus 1 by n. And I know the limit of this thing is 1. But that is because neither of these numbers is ever becoming 0. So had they in this question mentioned that a sequence of positive real numbers, if they would have just added this word positive here, or non-zero, even non-zero would work. Real numbers converges to x, then this would become. It's a very technical question. Very, very technical.
And in case the number is 0, like xn tends to
Yeah,
0,
consider this.
so
No,
it will
not
be
xn
not
tending to
defined.
0.
The
Yeah,
sequence is
yeah.
0, consists
What
0.
any of the elements of the sequence become 0. If the limit is 0, that is not a problem. Like I told you in this example. Where is that example? Like I told you in this example, the limit is 0, but that is not an issue. The sequence of the ratio sequence is still defined. So here only
Okay.
statement 2 is correct. There are a
Okay,
bunch of
sir.
other problems here. If you want to do, if you could copy this thing, yeah, I cannot copy it now. But you can basically go here. I just found some more problems from IIT, so you can log on to this website and see some more problems if you want.
Also, sir, if you could please explain 1 2 problems for the from the sequences to problem set, the convergence problems. Sir, I was only able to do part B from it.
Okay. 1 by 1 plus n square plus 2 by 2 plus n square and so on. So what we see is that the nth element is 1 plus 1 by n square, right? Yeah, nth element is sum of all these numbers. The sum of n elements going from here to here. Okay. So what he's saying is that the element xn is sandwiched between two different elements. What are these two different elements here? So the first element is you take the base as n plus n square. So xn is, what is xn? 1 plus 1 by n square. So 1 upon 1 plus n square plus 2 upon 2 plus n square plus 3 upon 3 plus n square and so on till n upon n plus n square. Okay, so he's saying that consider a sequence yn in which the elements yn are where have the common denominator. So instead of going for n plus n 3 plus n square and so on, just go for 1 upon n plus n square plus 2 upon n plus n square plus 3 upon n plus n square and so on till n upon n plus n square. So for any value of n which is going to be larger, xn or yn?
xn.
Xn is going to be larger because in yn every denominator is correspondingly larger. The numerators are same, denominators are larger. Okay, so n upon n plus n square is greater than, sorry, n plus n square is greater than 1 plus n square and so on. So all these denominators, corresponding denominators are larger. So xn is greater than yn. And consider another sequence wherein you take the denominator as 1 plus n square. So consider this sequence now, Zn, where all the denominators are 1 plus n square. So comparing Zn and Xn, which is going to be larger, Xn or Zn?
Zn.
So Zn is greater than Xn is greater than Yn. Right? So this much is established that for all values of n, this relationship holds. Now let us look at the limits of these two sequences. So this here I can apply summation n formula. So Zn becomes equal to summation n upon 1 plus n square. So n into n plus 1 by 2 times 1 plus n square. Basically, it looks like this, n into n plus 1 by 2. So I have taken this 2 here, right? So this becomes n square plus n upon twice into n square plus 1. Then you can divide both the numerators and denominators by 2 by n square. Okay, so to find limit, I'm going to find limit n tending to infinity Zn is basically limit n tending to infinity n square plus n upon twice into n square plus 1. I don't want to use L'Hopital. If you want to use L'Hopital, fine, if you know it. But till this point, I've not taught L'Hopital, so it will be wrong if I told you a solution which involves that. So if I don't want to use it, I'll just divide numerator and denominator by n square. So this becomes limit n tending to infinity n square by n square plus n by n square upon twice of n square by n square plus 1 by n square. Right? So this becomes 1 plus 1 by n. So you see that this limit becomes 1 by 2. Right? You can solve this now. This limit will become 1 by 2. Similarly, you look at this sequence yn, apply the same formula. So you will see that yn will become n into n plus 1 divided by 2n into n plus 1. N square plus n is n into n plus 1. So this just becomes half. So yn is the sequence of halves. So the limit yn will be equal to half. So now this Zn sequence is tending to half. This Yn sequence is tending to half. So the Xn sequence, which is sandwiched in between them, has no option but to tend to half.
So, sir, how do we get the idea, like which theorem we do?
I don't
do we have
want
to apply?
you to think like that. How do you get the idea? I keep telling you guys the only way to get idea is solve problems. So my job is to give you problems. You guys try to solve them. You can't solve them, mark them that you were not able to solve this problem. Come back to those problems after 10 days or a month, whatever time you can, and then again try to solve them. If you still can't do it, keep them marked in your notebook. Keep coming back to them till the time you are able to solve them. That's the only way. Okay, experience. That's the only way.
Sir, also if you could please give a bit elaborated hints for these questions. I want to try them, but I'm not able to solve them at all. These convergence problems.
Okay.
So if you could please give a bit explained hints or something of that
All
sort.
right, fine. I'll try to make video solutions for them.
Okay, sir.
These are hints, okay? You will have to think about them. These are not complete solutions. The whole idea is that even if I give you a hint and you work on it, you will still be learning a lot. Anyway, I'll give you solutions if that's what you want. But you have to, I know you will, but that is the thing that you will have to keep coming back to questions that you were not able to solve. So that is the only way. Fine.
So can I also ask questions from topology, past years?
Yeah, sure.
So just a second. So first two questions from past years, 2006 and 2007.
Okay, so this is a disguised topology problem, basically. So they don't talk about open sets and closed sets directly. Okay, so consider a society that consists of individuals who may belong to various sets called families or gangs. So society is basically set R, set of real numbers. And one of families or gangs implies open set or real, open or closed. So the idea is when they gave this question, probably nobody was able to solve it. But now you see that DSC does this thing. Yeah, they have done it multiple times. So when you see a very vague looking question like this, you have to think in the direction of topology. Now, which of family or gang represents open set or closed sets will be clearer from here. So the collection of families and gangs satisfy the following rules. The entire society is a family. Okay, so I have two possibilities basically here. Either families is open set and gangs are closed, or families are closed sets or gangs are open sets. These are the two possibilities that I have. Okay, the entire society is a family. So I know that a set of real numbers is both open and closed. So this does not give me any further information into solving this conundrum. That which represents families represent open set or families represent closed sets. The empty set of the society is also family. I know that the set phi is also both open and closed. So again, no extra information. Given the collection of families, the set of individuals who belong to every family in that collection is also a family. Okay, so given a collection of families, so let's say families are open set. So replace the word families with open set. So given a collection of open set, the set of individuals who belong to every family. So this is basically X belonging to intersection of all open sets, S, open sets. Okay, individuals who belong to every family. So this is every family means intersection is also a family, right? So what he's saying is that if you consider families as open set, then what he's saying is that intersection of a set of families should also be a family. That is, intersection of a bunch of open sets should be an open set. Okay, so this is finite or infinite. So let us go back to the definitions I have, which I told you are very important definitions.
So the intersection of finite is open and infinite is closed. Is
Okay,
not defined. It
okay,
can be
wait.
open or
Yeah,
closed.
very good. You remember it? That's good. I don't. I'll have to build the. I can always remember it using an example, but again, I'm not giving the exam, so uh, you remembering is it is much more important. Anyway, arbitrary union is union. A finite intersection is open. So obviously, he's saying that all types of intersection of families are a family. So family cannot be an open set because this is true only if this intersection is finite. He's saying that any collection of families is a family. So family cannot be an open set. So family has to be a closed set. So let us go with that idea that families are closed set, which means gang should be open set. So let's go ahead with this assumption and see that we do not come to any contradiction. Given any two families, the set of individuals who belong to either of the two families is also a family. So he's saying that if families are closed sets, then union of two closed sets, that is C1, C2, is a closed set. This is true because finite union of closed sets is always closed. An infinite union of closed sets can be open, right? So this does not go against what I know about open and closed sets. So this is no problem. Fifth point is a set of individuals is called a gang. Gang, according to me, thing is no. Yeah, families are closed sets. So gangs are open sets. So open. A set of individuals is called an open set if and only if the set of individuals not in it constitute a family. So this is saying that the complement of an open set is closed. So, okay, fine. This is also correct given this definition. Okay. So once you have figured out that families are open or closed, then you can do the remaining problems. So this next problem is intersection of two gangs is necessarily. So a finite intersection of open sets is always
Open.
open. Yeah. So a finite intersection of open sets is always open set. So gangs are open sets, so it should be
Yes, sir. I'll try the remaining questions a bit
okay.
now. Yes, sir.
And this one is going to be similar. Now,
Yes, sir.
instead of families and gangs, they write clubs and tribes. So very similar problem. So they can give you some other keywords here next time. Okay.
Yes, sir. So also one more question. Question number 40
From
from 2016.
round
Problem
16, problem
13.
number
Problem 13.
13.
Yes, sir. Yes, sir.
a continuous function is defined on an open subset of R, then the set is necessarily
So I was able to do this
okay.
question.
Okay, so this is a property which I have not talked about. Maybe I should have talked about. The a set a function is continuous if for all open sets E belonging to R. Okay, a function f defined from R to R is continuous if for all open sets E in R, f inverse of E is also an open set. So you talk about any function f. This is x, this is f of x. You take any open set in the codomain, the corresponding set in the domain, which you can plot from the inverse of this function, this should also be open. So you start with an open set here, you should end with an open set. This relationship is not true. That if you start from open, you should end in open. That is not true. But if you start from an open in the codomain, then you should end with an open set in the domain. Okay, so starting from here, you should reach an open set. The reverse relationship is not necessarily true. I used to do it, but I mean, for this one problem, there is too much theory which is involved. Uh, there are a lot of tidbits about topology, a lot of properties. We cannot do entire topology. Problem is, topology is a complete course, and there are going to be these weird things which they can ask from it, and we can never do entire topology. So what I'm trying to do is focus on things which are more likely to be asked and leave out things which are asked like once or have never been asked. So that way we don't clutter our brain with a lot of knowledge. We can focus on things which have a high likelihood of being asked. So that's the thing which you need to do here. If you know it, then yeah. So if function is continuous, E is an open subset, then this set just defines F inverse of E. So this is necessarily open. Okay. So one rule of thumb would be maybe build examples. Build examples and try to uh, eliminate things. So here what he's saying is consider any open continuous function. So the simplest continuous function that you can consider is f of x equals to x. Consider this function. And take any open subset of R. So consider simplest open subset. Give me a very simple open subset of R.
0 to 1 open
0 to 1.
subset.
Very good. Okay. Now, all the values of x such that f of x is going to lie in E. So you have given me this subset 0 to 1. This is my f of x graph. You have given me this subset 0 to 1. So what is the values on the x-axis for which f of x will lie in this range?
So could you please repeat what you just said?
So this set is defined as all values in the domain such that f of x lies in the set that you gave me. So tell me for what values on the x-axis will f of x lie in 0 to 1 set for f of x equals to x?
0 to 1
Very good.
open.
Okay. So we call it as f inverse 0 to 1, which is 0 to 1, which is an open set. Okay. So now consider that you have constructed this example without knowing anything that I just told you. Right. So I have not taught you this property. So I'm telling you how to do these problems without knowing this property. So now 0 to 1 is open, yes. Closed, no. Neither open nor closed, no. Open and closed, no. So just by building an example, you can solve this problem. You don't need to know the theory. Okay.
Yes, sir.
Right. So you will see a lot of such problems. So I cannot teach you everything. That is not possible given the limited amount of time that we have. We cannot learn everything. But the good thing about DAC is that when they ask a question like this, it is mostly possible to do it with the help of an example. So you consider an example and try to do it. A lot of students would just lose hope at this point, like, "यार ये क्या है? I don't understand. ये तो पढ़ाया ही नहीं है." They will ask questions like that. Okay. So if it comes, maybe don't do it right away because you do not know that if an example will work or not. Because if they give none of the above here instead of, let's say, D option, they give D option as none of the above, then you can never be certain. So whenever you see none of the above as one of the options, don't work with an example, because an example can give you open in some situation, but some other example can give you closed. Right. So these are tricks of handling objective problems. So if the D option was none of the above, maybe don't do it. If you feel like you have a lot of other problems to do, don't even try building an example. Don't waste your time. Uh, do the other problems where you are certain you can get an answer and come back to this one later. Okay.
Okay, sir. So the question which is just above it. Yes, sir, this one.
Let n is the set of natural numbers. Suppose there's a bijection between n and x. Suppose there's also a bijection between n and y. Okay. So if there's a bijection between n and x, you know that cardinality of n is same as cardinality of x. Right. So what we can say is x is countable. Similarly, there's a bijection between n and y, so y is countable. So if x is countable and y is countable, x in union y is also countable. Because of this property that we did, that where is that property? Okay, we did it in cardinality, a countable union of a countable union of countable sets is countable. We did this in sets and functions when we were doing that. So if x is countable and y is countable, then x in union y is also countable. I should have given this in set theory. Anyway, you already know set theory, so you should know countable also. So countable union of countable sets is also countable. So if x union y is countable, it basically means that there will exist a bijection between n and x union y. In fact, it is going to be countably infinite. So any set is countably infinite if there exists a bijection between a set of natural numbers and that particular set. These both sets are countably infinite. So a union of two countably infinite sets is going to be countably infinite. So that's why x union y and n will have a bijection between them.
Okay, sir.
Okay. Next.
So done. Like all the doubts are clear now. Can I
So
also ask doubts from limits or maybe in the next doubt
maybe next
lecture?
time. I'm feeling a little tired. So
Okay, sir.
we'll do it next time.
Okay, sir.
Okay. All right. I will end this class now. And
Thank
I'll
you,
see
sir.
you on Saturday. Bye.
Okay,
Welcome.
sir.